Okay, so I'll start by thanking Cody and John for letting me present my work here and for organizing this seminar series. So today I'll be explaining some computational advances we've made for exploring the Kreuzer-Skarke database, and I'll be showcasing our open source package CYTools, which we expect to release soon. This is work done in collaboration with Mehmet Demirtas and my advisor Liam McAllister. So this is a quick outline of the talk. I'll be giving some motivation and background. I'll describe our new algorithms and computational advances. I'll show a short live demo of our package CYTools, and then I'll conclude. So as all of you know, there's basically two main approaches for studying string theory. You can either study what sorts of things cannot arise in string theory, namely you can study the swampland, or you can study the things that do happen in string theory, namely you can study the landscape. Today, I'll be focusing on a specific corner of the landscape that is particularly well understood, namely Calabi-Yau compactifications of string theory, which it might only be a small part of the landscape, but it's still very rich and very interesting. So if we're gonna make any sort of systematic studies of the Calabi-Yau landscape, of course, we're gonna need lots and lots of Calabi-Yaus. And for this, we're going to use materials construction of Calabi-Yau threefolds, which as we'll see, will give us lots and lots of Calabi-Yaus. So just as a quick reminder, the way this works is that you take a 4-dimensional reflexive polytope, then you find a special kind of triangulation, a fine regular star triangulation, which I'll review later. Then you interpret this triangulation as defining a fan, and then construct the corresponding toric variety. And then finally, you take the anti-canonical hypersurface on this toric variety, which is going to be a smooth Calabi-Yau threefold. So clearly, our starting point here are reflexive polytopes. So let's see what that is. So as a reminder, a lattice polytope is reflexive. If it's dual, it's also a lattice polytope. And Kreuzer-Skarke found all of the 4-dimensional reflexive polytopes. There are almost 474 million of them, and they constructed their famous database. They also gave us this really nice package called pulp, which handles polytope computations. But pretty much for the rest of the Calabi-Yau construction, we're left on our own. Although there are some mathematical software packages like Sage that can be used to do this construction. Okay, so if there's already some software out there to do this, why am I talking about this? Well, the thing is that the complexity of the database grows exponentially with the number of points on the polytope, which roughly corresponds to H11 of the Calabi-Yau. And there's reason to believe that at large that most of the landscape, the Calabi-Yau landscape, lies at large H11. So here, there's a plot on the number of Calabi-Yaus per polytope as a function of H11. And as you can see, the numbers up here at large H11 are gigantic. And even though this is only an upper bound, we still believe that the actual number of Calabi-Yaus up here is gigantic. And for context, in 2014, it took an immense effort and over 100,000 CPU hours to extract the information of the Calabi-Yaus with H11 less than or equal to 6, which is this red region over here. So clearly, if we are going to study the entirety of the database, and specifically the large H11 section of it, we're definitely going to need new software packages. So even though Pulp and Sage are fully powerful packages, we just had to abandon them and write everything from scratch. This is what we did. And we put together all of our tools into a package that we call CYTools, which we expect to release soon. So some of the key ingredients that we'll need to handle if we're studying the Calabi-Yau or Calabi-Yau threefolds from the KS database are the following. We're of course going to need to handle reflexive polytopes. We're going to need to find triangulations of those polytopes. We're going to need to compute intersection numbers of the resulting Calabi-Yaus. We're going to need to compute Kähler cones of the Calabi-Yaus. And we're also going to try to randomly sample Calabi-Yaus from the KS database. So I'll go through each of these and explain what we've done for each. So first, let's start with reflexive polytopes. So as I mentioned, pulp has been sort of the go-to package for polytope computations. And that's even for recent large-scale scans of the database, such as the one by Wally Taylor and his student, where they try to find reflexive 2D subpolytopes in all of the polytopes in the KS database. But as I mentioned, we decided to abandon pulp and instead write our own algorithms. So what we did is that we used QHO and PPL, some code by Volker Brown, and quite a bit of additional optimizations so that we can compute the lattice points of the polytopes. And we also devised a pretty optimized phase algorithm for four-dimensional polytopes. So I should mention that pulp is actually still better in some cases, for example, for higher dimensional polytopes or things like that. But for the specific case of four-dimensional reflexive polytopes, our algorithms are much, much better. In fact, the end result is that our Python code is about 4 times faster than pulp, so keep in mind that our code is in Python, whereas pulp was written in C. So in fact, if we transcribe our code to Julia, it is now about 40 times faster than pulp. So in fact, we're able to compute all the points and all of the phases of all reflexive polytopes overnight on a personal computer. In fact, I did it with my computer that I'm currently using. Okay, so clearly we have reflexive polytopes down. Now let's look at triangulations of those polytopes. So as I mentioned, we need to find a special kind of triangulation. We need the triangulation to be fine, regular, and star. So here, star simply means that the origin is a vertex of all the full dimensional simplices in the triangulation. And this is so that we can interpret the triangulation as defining a fan, which we use to construct the toric variety. Fine means that the triangulation uses all the points, although we can actually exclude the points interior to facets. And this is so that the singularities of the toric variety are mild enough so the Calabi-Yau hypersurface is smooth. And finally, regularity is a bit more tricky to explain, so I'll go into that in a bit more detail. And this is going to be needed so that the toric variety is Kähler, which is a structure that the Calabi-Yau will inherit. So let's look at it more carefully. So triangulation is regular if it can be constructed in the following way. You take the points that you want to triangulate and you lift them up into one extra dimension by some set of heights hi. Then you construct the convex hull of this new point set. And finally, you take the lower faces and project them down to obtain the triangulation. This is by far the hardest property to check for these triangulations, and it's partly responsible for why it's so difficult to study Calabi-Yaus with large H11. So the typical way of finding FRSTs has been with the Tascon package, which is a pretty nice piece of software. But if you want to find regular and star triangulations, it really starts to struggle, even at moderate H11. And at some point, it just can't do it anymore. So instead of constructing triangulations and then checking if it's regular, which is the really hard thing to do, what we're doing instead is that we use the previous construction I just mentioned so that we obtain triangulations that are regular by construction. We use Siegel or QHO to perform this process, and it is quite quick. So now that we have regular triangulations, how do we make them star? Well, that's pretty simple. All we have to do is that we take the height of the origin and we pull it down much lower than all of the other heights, and the triangulation becomes star, as in this example. And then finally, to ensure that the triangulation is fine, we can simply pick a reasonable choice of heights, which is not too hard to do. And the end result is that we can obtain triangulations extremely quickly. So here's a comparison. Whereas in 2014, for H11 of 25, it would take a few hours to find a triangulation. Now we can find the triangulation at the largest H11 of 491 in about 20 milliseconds. So that's quite an improvement. The only disadvantage of this method is that we can't completely enumerate all of the triangulations as you would be able to do with Tascon. But since triangulations grow exponentially with H11, this would be impossible with Tascon, so this is not much of an issue. Okay, so now we have polytopes and triangulations done. Now let's look at how we would compute intersection numbers of the Calabi-Yaus. So the typical way of finding intersection numbers of Calabi-Yaus would, for example, be using Sage. But if you do that, it really starts to struggle, even for moderate H11. And at some point, it just becomes unusably slow. So luckily for us, Max Stillman, who is a mathematician here at Cornell, explained to us that there's a pretty simple and computationally superior algorithm, which is not new, but it was unknown to us. All you need to do is that you first compute intersection numbers of distinct divisors using the full dimensional simplices of the triangulation. And then you can use the linear relations of the GLSM charge matrix to construct and solve equations for intersection numbers that involve self-intersections. We perform lots and lots of optimizations on this algorithm, and the end result is that we can compute intersection numbers extremely quickly. So whereas in 2017, for H11 of 100, it would take us about half an hour to compute the intersection numbers. Now for the largest H11 of 491, it takes about 2 or 3 seconds. In fact, I think now it's like 1.5 seconds. Okay, so now we also have intersection numbers done. Now let's look at Kähler cones. So it's pretty well known that finding the exact Kähler cone of a Calabi-Yau is very difficult, and there's no known algorithm to do it in general. So a common way, a common approximation that is used is to use the Kähler cone KV of the ambient variety, which is going to be contained in the Kähler cone of the Calabi-Yau. And this KV can be obtained by well-known algorithms by Park, which was further refined by Berglund, Katz, and Clem, and it can be done pretty quick. The thing is that there can be multiple triangulations, or in other words, toric varieties, that give rise to the same Calabi-Yau. So for example here, if we have a bunch of Kähler cones, this is just a cross-section of them, and there can be multiple of them, well, Kähler cones of ambient varieties, and there can be multiple of those ambient varieties that contain the same Calabi-Yau. So it would be ideal to glue them together to approximate the Kähler cone of the Calabi-Yau better. So we define this K union to be the union of all the Kähler cones of the varieties that contain the same Calabi-Yau. And it's going to much better approximate the actual Kähler cone of the Calabi-Yau. This is an actual example of how this happens. So this is a 2D slice of the secondary fan of the largest 4D reflexive polytope. So here, each colored region is the Kähler cone of a different toric variety. And just as a quick side note, to render this image, we had to compute 16 million triangulations of the largest reflexive polytope, which a few years ago would have been impossible. Okay, so now let's say that we're looking at some Calabi-Yau that sits over here. And let's see what happens if we glue all the Kähler cones of the ambient varieties with the same Calabi-Yau. So we see that we get a much larger region. And if we perform the same procedure for the rest of the picture, we obtain this. So now here, each colored region is the K union for some different Calabi-Yau. Okay, so now how do we explicitly compute this K union? Well, at small h11, this can be done simply by finding all the triangulations that give rise to the same Calabi-Yau, and then gluing all the KVs manually. The problem is that this quickly becomes impossible since the number of triangulations grows exponentially with h11. So, but with the good understanding that we've gained of the secondary fund, we actually managed to extend the previous algorithm so that we can compute K union directly, even at large H11. But this is still work in progress. At small H11, we have verified that our algorithm matches the brute force computation of just gluing everything together. At large H11, everything looks good so far, but we're still making sure that there are no issues. So this is probably not going to be included with the initial release of CYTools. And then lastly, let me talk quickly about randomly sampling Calabi-Yau from the database. So since the number of possible triangulations of polytopes and large H1 is astronomical, it's kind of difficult to obtain a first sample of Calabi-Yaus. And hereby for I just mean that the distributions of topological quantities or anything you'd be interested matches the distribution of the full set. What you would normally, like one way you could try would be by starting with some initial triangulation and then randomly performing by stellar flips. However, this is very slow and it actually doesn't produce a very good sample of the set. So what we did instead is that we combined random walks in the secondary fund with random by stellar flips. So in other words, we start some random triangulation, we pick some random direction until we find the triangulations become non-star or non-fine. We pick a point randomly in between. Then we perform a few random flips, and then we repeat the process. We showed that a small H11, this actually produces a representative sample of the full set of triangulations. And we believe that this also works at large H11, where we can't verify that this is the case. Okay, so now this is all done. Now, I am going to show you a quick live demo of our package CYTools so that you can see that it's quite easy to use. Let me do that. So we'll be distributing our package in the format of a Docker image so that it's very easy to install in any operating system. And it's mostly in Python so that it's very easy to use. So here I'm just importing the polytope class and the fetch polytopes function. So you can use these fetch polytope functions to directly fetch polytopes from the KS database so that you don't have to keep anything stored on your computer or anything. So in this example, I just got some 4-dimensional polytope. We can also construct polytopes by inputting a set of points. You can see it just says that it's a 4-dimensional reflexive polytope. We can compute various things of the polytopes in pretty intuitive ways. So for example, we can find the list of points or the list of 3-dimensional faces. We can also obtain triangulations of the polytope with the triangulate function, which takes quite a bit of parameters, but by default, it just randomly returns a fine regular star triangulation of the polytope. So here it says that it's fine and star. By default, regularity is not checked since it takes a bit more time, but you can check it with this regular function. And now it says that it's a fine regular star triangulation of the polytope. You can then get the corresponding Calabi-Yau with the get CY function. And you can compute various things of the Calabi-Yau with pretty intuitive functions. So for example, you can compute the GLSM charge matrix, you can compute the Morricone. So here, if you want to print the rays of the Morricone, you can use the rays function. You can also compute the intersection numbers of the Calabi-Yau. So for example, here, this would mean that kappa 126 is equal to 1, and so on. And then lastly, just to show the power of the package, I'm using the largest 4D reflexive polytope and computing all of its points, all of its faces, and finding a triangulation, constructing the corresponding Calabi-Yau, and then finding the Hodge numbers and the Euler characteristic of the Calabi-Yau, computing the GLSM charge matrix, computing the Morricone, finding all intersection numbers, and I'm timing the whole thing to see how long it takes. So keeping in mind that this computation would be impossible to do in Sage, whereas here it just takes a few seconds, 5.5 seconds. So that's quite a bit of an improvement. Okay, so now let me go back and conclude. So in conclusion, we have developed tools that not only significantly outperform previous packages, but allow computations that were straight up impossible to do in things like Sage. We'll soon be releasing our open source package so that everyone can explore the Kreuzer-Skarke database with this, so that you can be an explorer like this. And we hope that our package will allow systematic studies of string vacua and to gain a better understanding of the landscape. If you want to be, so we'll release this pretty soon, but if you want to be a beta tester now, you can contact either Mehmet Demirtas or me. Thank you.
All right, thank you, Andres, for the very nice talk. Let's all thank Andres using our clap emoji. Are there any questions for Andres? At least to get things started, I have one. So I know some of this is optimized for 4D, but what are the prospects of also including 5D reflexive polytopes in this code?
Yeah, so actually most of the things already work for 5D. We would have to adapt
Fantastic.
a few of the things for 5D, but yeah, it should be pretty straightforward. And yeah, we have that in mind for the future.
Great. Okay, I think there's a lot to explore there, so that would be really cool.
Yeah.
Ling.
Hi, thanks for the talk. I have a question regarding open or half polytopes, essentially like tops. Can you also do computations with those? I mean, sometimes it's helpful actually to say keep like in a vibration structure the base generic and just study intersection properties of the fibril divisors.
No, I mean, it currently doesn't support something like that. But
so basically the polytope you have to feed in has to be convex.
Yeah.
To even start, say, computing a triangulation.
Yeah.
I see. Okay.
Well,
I mean, if
hard to adapt.
Yeah. Well, I mean, if just as a suggestion, then maybe if you could build something like that into there, that'd be kind of nice, at least for my things I'm interested in. But anyway, thanks.
Thank you.
Next question is from Fabian.
Hey, Andres, thanks for the talk. Can you explain a bit more what you mean by the sampling produces so when you randomly generate triangulations, you get a representative sample. So you mean that the induced distribution of triangulations is drawn from a flat prior?
Yes. So we're using just like a counting measure. So that, I mean, yeah, like we're weighting every triangulation as like one.
Okay, so you assume like a flat distribution and you check whether you get sort of from all points in this space some distribution, some sampling. In other words, you get the same sampling as you would have expected to get if you were just completely drawing sort of random with equal probability.
Yeah.
Okay. Thank you.
Okay, if there are no further questions, let's thank Andres one more time.